Thank you. I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you guide our work today, Lord. In your name I pray. Amen. So today, I need to talk to you guys about something called the Quotient Group. And this is a way of building new groups from existing groups. In some sense, it's a way of dividing a group by one of its subgroups, if that makes sense. Well, we'll explain in the sense in which it makes sense here shortly. So to start with, a cautionary tale about what happens if you try to do this construction that we're going to go over for something that doesn't meet the condition of normality. So here's S3, and we can look at the subgroup H. And the subgroup we can look at is the subgroup with 1 and 1, 3. Right? If we look at this subgroup of order 2, then we get 3 cosets, right? So we can look at the left H cosets, and we can look at right H cosets, and we can see what those are. So this is instructive, if nothing else, just because you guys need more practice with how to denote and understand what cosets are, right? So, of course, we can talk about the identity times H, which is just going to be H again, right? And it doesn't matter if you do on the left or the right, both the identity coset is just the coset again, like the representative. On the other hand, if we do 1, 2 on H, that means 1, 2 times 1 and 1, 2 times 1, 3. What's that work out to? Well, 1, 2. And what's 1, 2 times 1, 3? Think about it. Let's see here. 1 goes to 3. And then 3 goes to, so that's 1, 3, 2. On the other hand, if we do H, the right coset, H with 1, 2 multiplying on the right instead of the left, that means we have 1 times 1, 2, and 1, 3 times 1, 2. Notice the distinction, multiplying on the right as opposed to the left. And, well, we're going to get 1, 2 again for the first multiplication, but the second one's different, right? What's that? Now 1 goes to 2, 2 goes to 3, so we get the 3 cycle 1, 2, 3. All right? And then finally we have, let's see here. So I've got 1, 2, 1, 1, 3. Let's see here, what's the next one I should look at? Perhaps 1, 2, 3 on H. Look at that coset. What do I got? I've got 1, 2, 3 times 1, 2, 3 times 1, 3. So that works out to, of course, 1, 2, 3. And let's see, what's 1, 3 times 1, 2, 3? 1 goes to 3, 3 goes to 1. So 1 is fixed, and 2 goes nowhere, 2 goes to, 2 goes to 3. Right? So if you look at the union of the things in the left column, we get what back? What's the union of all the elements that you see in the cosets, the left cosets? The H, this thing, and that thing. Taken together, this, and that, put together give us all of S3, right? That illustrates that the left cosets partition S3 into 3 equal-sized cosets, each with 2 things in them, right? So the index of H is what? Lagrange's theorem says it's the order of S3 divided by the order of H, which is 6 over 2, which is 3. Right? Just like we saw these 3 cosets, each of them has 2 things in them. All right, finally, H times 1, 2, 3, what's that work out to? Well, 1, 2, 3, and then 1, 2, 1, 3 times 1, 2, 3. And we calculate, we got 1, 2, 3. And then what does that work out to? It must be 1, 3, 2 by process of elimination. 1, 2, 3, is that right? Oh, yeah. Wait, no. That's not right. I shouldn't do. Oh, I'm sorry. I've forgotten. I have to look at. Oh, I'm sorry. Look, I don't. This is a fussy thing. Look, we can also say that this is equal to h times 1, 2, 3. Yeah. And we could also say that this is equal to 1, 3 times h. This is also equal to 1, 3, 2 times h. This is also equal to 2, 3 times h. See, either we have two representatives for each coset, yeah? And the thing is, I can't look at h times 1, 2, 3. I mean, I could, but I already did. That's that's already covered, right? So to compare, I actually need to use h 2, 3 down here, otherwise it's not interesting. So I should look at h times 2, 3 to get something worth looking at here. And so that gives me 2, 3. 2, 3 times, well, 1, 3 times 2, 3, which is what? It's going to be 2, 3, and then whichever cycle I haven't covered yet, which is what? I think that should work out the 1, 3, 2. Let's see how it goes. I put in 1, goes nowhere, goes to 3. I put in 3, 3 goes to 2. Put in 2, 2 goes to 3, goes, yeah, it's 1, 3, 2. This is the 1, 3, 2 cycle, this product. Again, the right cosets partition the group. Each one has 2 things in it, and you get everything, right? So I hope this is perhaps helpful. I mean, we could also say that this is equal to h times 1, 3, 2. This is the subtlety with cosets, is that we have not a unique representative, right? You have as many representatives as you have elements of the coset, right? Okay, well, you agree with me or not, it's true. So suppose we try to multiply cosets, right? Try to multiply cosets. By the natural rule. What would the natural rule be? The natural rule would be a times h times b times h. Well, how about we just multiply the representatives, right? Is that going to work for us here? Well, that's the trouble. We can look at, for example, 1, 2h times 1, 2, 3h, right? Which would, according to our natural rule, be 1, 2 times 1, 2, 3 times h, which would be what? 1, 2 times 1, 2, 3 works out to 2, 3. So it's that left coset. On the other hand, what are other ways we could look at 1, 2h? We could also look at 1, 2, 3h by what? Is that right? 1, 2 times 1, 2, 3, what's that give us? Let me work that out for a second here, guys. What's that? 1 goes to 2, 2 goes to 1, 1 is fixed. I think that's the product, right? So the trouble we're going to get into is if we use a different representative, I believe. So 1, 2, we could also write as 1, 3, 2, right? These are supposedly equal, right? They're both this right here, right? What happens when we take that times 1, 2, 3, h? What happens? We get 1, 3, 2 times 1, 2, 3. What happens with that? 1, 3, 2 is really 3, 2, 1. Those are inverses. So we just get EH, or just H again, right? So the product of A, H, and B, H depends on our choice of A and B, which means this is not a binary operation, right? I mean, because we take two inputs, and how many outputs did we just produce? Not one output, but at least two outputs, right? So this shows you that if we have a subgroup like H here, right, a subgroup for which the left and right cosets don't match, then we cannot multiply by multiplying representatives. Do you see the problem? I hope you see the problem. The point of this example is to show you why we have to make the definition which follows. So, and also because I just think it's good exercise to do some calculations with cosets, yeah? So definition, H, a subgroup of G, is said to be normal. And let me if and only if A, H, A inverse is a subset of H for each A and G. We indicate normality of H by writing that H is like this. So we basically close the inequality, make a triangle there like that. H is a normal subgroup of G is what that notation means. All right? So, comment. The condition AH, A inverse is a subset of H implies, well, it's equivalent to saying that AH is equal to HA for all A and G. Right, this for all A. That for all A and G is equivalent to saying that the left and right cosets of H match for all A and G. I'm stating the definition as I am to make our life easier, because for proofs and problems, the condition which I wrote down is often easier to verify and is in fact logically equivalent to the fact that left and right cosets match. All right? And I think that's an immediate consequence of like the list of things we proved last class. Didn't I prove that AB is equal to, oh, maybe not, but it's a similar thing. Anyway, I'm going to go on. That's a good exercise for you to try to work through, prove the equivalence of these statements, yeah? Okay, so let's look at some examples. First of all, if G is abelian, then, A plus H is equal to H plus A for all A and G, right? Thus, I'm assuming here H is a subgroup of G, yeah? Thus, every subgroup of an abelian group is normal. So every subgroup of an abelian group is normal. Of course, you could also look at it in terms of the definition. What would the definition look like? What would A, H, A inverse look like in the additive sense? A plus H minus A, right? I mean, maybe that's worth writing down. I don't know. A plus H minus A. That would be the analog of AH, A inverse in the additive sense, yeah? And that is literally the set A plus H minus A such that H is an H, right? Which is precisely what? H, such that H is an H, which is otherwise known as? H, yeah. So equality certainly gives us that it's a subset. Yeah. All right. Another example. I talked about SL NR, which is a subgroup of GL NR. Let me remind you what those are. What was SLN? Determinant 1, right? Yeah. So a typical coset here would look something like G SLN, right? Would be something like GA, such that what? The determinant of A is equal to 1, yeah? And G is an element of GLN. Okay, so let's just, let's pause here for a second. How would we prove that SLN is a normal subgroup? What do we have to do here? Let's do it. So let's let G be an element of G. I tell you, I'll use A just for the sake of matching my definition. Let A be an element of G, LNR, right? And let's and consider X an element of A, SLN, are A inverse, right? Hence, there exists, let's say, B in SLN such that what? X is equal to A, big B, A inverse. What do we know about the determinant of little a and the determinant of big B? We know that the determinant of little a, it's non-zero. That's what we get for it being in big GLN, right? It's an invertible matrix. It has non-zero determinant. Determinant of B, we know is what? It's 1. So we calculate the determinant of X is equal to the determinant of ABA inverse, yeah? Which is the determinant of A times the determinant of B times the determinant of A inverse, right? But you remember the properties of determinant. We can just as well write that as determinant of AA inverse times determinant of B, right? And this is 1, and that's 1, so it's all 1. The determinant of X being 1, what's that say about X? X is in the special linear group, right? S is in SLNR. Which proves what? We picked a point in the conjugate of SLN by A and A inverse, right? And we just showed that that point is also in SLN. That point X was arbitrary. Therefore, we have shown that A SLN, A inverse, is a subset of SLN. Therefore, SLNR is a normal subgroup of GLN. There you have it. direct from our definition, the proof. All right, another example we could look at. Let's look at the dihedral group, right? The dihedral group is an interesting group. We have Dn, and let's think of it as being generated by A and B, such that the order of A is n, the order of B is 2, and how's it go? B, we could say BAB equals to A inverse, like that. That's a decent way to generate it, right? And we have shown, what do we know? We know that A to the power j times B is equal to B A to the minus j from our previous work, right? Previous encounters with this beast. So this we know. What's an interesting subgroup to look at? How about the cyclic subgroup generated by A? Right, that's a subgroup. We can look at H equal to the subgroup generated by A, which has got what? 1, or I guess I've been using E, haven't I? E, A squared, A to the n minus 1. So what's the order of H? It's n, right? So how many cosets? How many H cosets do we have? How many? We just have 2, right? By Lagrange's theorem. And those cosets are H. And how about BH? Are the left cosets. Is H a normal subgroup? What are the right cosets? So as you enumerate left or right cosets, we always have a copy of the subgroup, right? So if you think about right cosets, you've got H, right? I mean, we could say or he, but those are just H and H, yeah? But what's the right coset? Well, it would be HB, wouldn't it? How do I know that it's HB? It's pretty simple. If I pick something that's not already represented in my subgroup, right, and look at the coset represented by that element, that has to be a distinct coset from the one I already have. And it also has to be as big as the one I already have, since the subgroup I'm looking at is half the size of the group. I know I'm done. Does that make sense? In fact, that gives us a theorem. If you have a subgroup which is half the size of your group, it's necessarily normal because there are just 2 cosets, and hence there are just 2 right cosets. And therefore, as they match at the groups, the left and right cosets have to match, which gives us normality. So this is a theorem. If H is a subgroup of G, and the index of H is equal to 2, then H is a normal subgroup of G. This example is just a showcase of that result, a more general result. All right? Okay. Now you could look at other subgroups of Dn, right? And they may or may not be normal. But that particular subgroup of Dn is normal. Oh, what's a good application of this? How about the alternating group? That's a subgroup of Sn. And the order of An is what? N factorial divided by 2, right? So therefore, An is a normal subgroup of Sn. So the set of even permutations gives us a rather well-known normal subgroup of the set of all permutations. All right? And example 3.27, I actually work out an analog of the example I started class with, except for A3 rather than this thing H. Yep.
So you can just prove that the index is half of the. You can just prove that the index is half. Is that necessarily proving that it's?
Well, remember, Lagrange's theorem says that the index is equal to the order of the group divided by the order of the subgroup. So if that's equal to 2, that means that the order of the group is equal to twice the order of the subgroup. I don't think that's your question, though. Is that your?
Well, all we did was prove that the order of AN was half the order of FN.
Yes, by that theorem. Yeah. Now that's special. Like usually we don't have something so nice as that, but if you have a subgroup which is half the size of your group, that means you only got 2 cosets. So again, it's necessary that the left and right non-subgroup coset be the same thing, which is all I need to get normality of the subgroup. So yeah. That is a special situation, though. It's not usually so easy. So theorem, here's the theorem. The theorem is that the thing I just erased, the natural rule for multiplying cosets, actually works to define a binary operation on the so-called factor group. What's the factor group? Or the quotient group of G by H? So definition, G mod H is equal to GH such that G is in G. All right. This is the set of cosets. All right. And here's the theorem. If H is a normal subgroup of G, then AH times BH equals to ABH defines a group structure on the set of cosets on G by H. We call this group the factor group of G by H, or sometimes we just say it's a quotient group, all right? It's a quotient of G by H. So to prove this theorem, we need to show that the injustice of the first example does not happen for a normal subgroup. Let's see why that is. So let's work on that theorem / definition. So let AH equal to A prime H and BH equal to B prime H, right? Consider. We'll start with A prime H times B prime H. What would we like to see that that's equal to? Right. I mean, this by construction. Well, the question is this equal to, AH times BH, right? We'd like to see that it doesn't matter whether you multiply primes or multiply unprimes, we get to the same result. So I'm going to try to show you a calculation here which proves that. All right, so how about this? We can look at this as A prime, let's see here. Well, how about A prime, B prime, H? H, yeah. I'm sorry, I'm forgetting the proper form of my argument. Give me a second here, guys. Let me not do that. That's not what I mean to write. All right, here we go. So this is, by definition, A prime, B prime, H, right? But what do we have? We have A prime, And what do we say about B prime H? It's equal to BH, right? And then what? Then this is A prime HB, right? Because we assumed that this and that were equal. And then we have HA, excuse me. Then we have AH because A prime H and AH are equal, right? And then, what do we do? Then I, again, flip the B and the H, so that gives me ABH, which, of course, gives me AH times BH. So you see, it doesn't matter. It doesn't matter which representatives I use for the cosets. We get the same product either way. The problem of the first example doesn't appear if we have equality of the left and right cosets, is the point. Yeah.
What are we assuming in order to switch B and H?
So this is because HB is equal to BH for H, a normal subgroup of G. And likewise, well, I guess that's what I did both places, actually, right? Yeah. And I'm also using the fact that we're assuming that AH is equal to A prime H and that BH is equal to B prime H, yeah? Okay, so that's the first thing, is that the operation, the natural operation, is well defined. And once you have that, the rest of the group the rest of the properties of the group are pretty straightforward to show. So at this point, we have a binary operation on the set of cosets. Next step, I mean, you pick what you want next. How about identity? What happens when we look at times AH? What's that give us? That gives us EAH, right, by definition, which gives us AH. But on the other hand, we could look at that as AEH, which would be AH times So you can see then that EH, which we could of course identify as H, is just H as a point set, is the identity for the quotient, yeah? The identity for the factor group is the subgroup. Subgroup itself is serving as the identity of the quotient group. Associativity wouldn't be difficult, right? What if we wanted to prove, so AH times BHCH, right? What is that? That's AH times BCH, yeah? Which is ABCH, which is ABCH, which is ABH, CH, which is AH, BH, parentheses, CH. So there you go. Associativity of the factor group follows, of course, from associativity of the group and the fact that we have associativity on the representative. How about inverse? If I have AH times A inverse H, what happens? I have AA inverse, yeah? Which is EH. So it follows that AH, the inverse in the factor group, is in fact just that again. So the inverse, if you want to find the inverse of a coset, you find the inverse of its representative in the factor group. Any questions? Comments? No, wait a minute, no. Don't want comments. Concerns? No? All right. So we got this factor group. It's kind of exciting. Yeah. Now, what's the order? What's the size of the factor group? What's the What's the order? How big is the factor group? It's the number of elements. Yeah.
So in the second step, we're proving identity and then associativity and inverse. What are we doing with the A prime H, B prime H?
We're showing that the operation even makes sense. We're showing that it is a binary operation, right? That it's closed on the set of cosets and that it's single valued. So, like the trouble with the first example was we tried to use the same rule, but it didn't work because we got two different outputs for the same input, which goes to show you this construction fails if we use a subgroup which is not normal. Yeah. On the other hand, if we try this construction in an abelian group, it always works because every subgroup of an abelian group is normal. So you can hardly go wrong there. Right? How big is the factor group? It is as big as the number of elements. How many elements are in the factor group? It is the set of cosets, right? How big is the set of cosets? That's what we call the number of cosets, also known as the index of H, right? So this is the index of H, G colon H like that, which we said by Lagrange's theorem was the order of G over the order of H, assuming, of course, that G is finite. So for a finite group, we have this amazing victory of notation that the order of the quotient is the quotient of the orders, which you probably could have gotten right without understanding any of this, right? So group theory is sometimes forgiving because mathematicians are kind in their choice of notation, yeah? All right. We have now gotten to the part of the lecture where I'm going to show you, is basically show and tell from here on out. So let me get off the projector. So the rest of the lecture is, I just have some examples of factor groups, yeah? So. Ooh. Mm-hmm. Let me get my laser. All right. Oh, thanks. I'll double check. There you go. Now we can't go wrong. So, all right. So this is an abelian group. Yeah. By the way, these I hope you study those. These are just these are comments from years past, right? I understand you don't have a copy of Galilean. Don't read too much into those. It is still the case that reading those relevant pages in Galilean would help you, right? The more you know, And I could leave a copy of Galilean in like, the math conference room or something if it'd be helpful to you guys. Should I do that? Okay, well, I will try to do that. It's a sort of teal-looking book. You'll see it. Okay, anyway, so if we have Z6 is that group, we can look at the subgroup generated by 3, which is 0, 3. Subgroup of order 2, which means we're going to have 6 divided by 2, 3 cosets. And here are those 3 cosets, H, 1 plus H, and 2 plus H. Right? Now, if you've got 6 cosets, right, and you're writing the Cayley table for a subgroup that has index 6, how many times are you writing plus H in your Cayley table? 36 times. Is there another common notation which would make your life easier? There is. So the other notation that's sometimes used is instead of writing A plus H, people might just write A bar. So you could use a bar for the coset. This notation's dangerous if it's misused, but in the bar notation, you know, A bar times B bar is equal to AB bar. But you got to understand that the notation for equivalence classes, right? And if we use the bar notation, you can't really tell if it's an additive or a multiplicative coset, can you? There's a downside to the bar notation, right? But at the same time, if you have a problem you're explicitly doing like a kabillion calculations in a coset space, maybe the bar notation is a good choice. You can use it in your homework if you like, just announce what you're doing and be clear, okay? So I don't think I don't think it even appears once in my notes, all right? But one of you asked me a question about your solution to one of the problems in mission. What is it? 4? 3? 5? What mission are we on? 4, the next one, yeah. So the next one, and I saw this is the C of plus H, plus H, plus H, plus H, and I had pity. And so that's why I'm making this comment. Bar can be helpful. Yeah. All right. So, you know, if I use the bar notation, it would be like 0 bar, 1 bar, 2 bar, 1 bar, 2 bar, 0 bar, 2 bar, 1, 0 bar, 1 bar. I'm going to shut up now. Anyway, as you can see, this is the Cayley table for the factor group of Z6 by H, and you can pretty clearly see it's just Z3 in disguise, right? So apparently there's an isomorphism Z6 mod this subgroup is Z3. If you look at the subgroup of order 3, generated by 2, 0, 2, 4, you have this Cayley table, right? And you can see that that's pretty much just Z2, right up to isomorphism. So just, you know, a couple examples to get us started. So there are some standard normal subgroups that are available for any group. One stupid choice is E. The trivial group is normal. All right. Another less trivial group for most groups is the center of the group. You can prove that the center of the group is a normal subgroup. That's probably a homework problem for you guys. Now, it may be that the center is equal to the identity. For example, for the group of permutations, all right, the group of permutations, I think the center is the identity. But on the other hand, for an abelian group, the center is the whole group, right? So there's a variety of, these inequalities may be strict or actual, and of course these inequalities are just subgroup relations, right? So here's the basic idea. The basic discussion here is that, you know, G by H or G mod H is a new group, right? And you can think of it intuitively kind of like fractions, right? You guys give me a fraction 3/6. You'd be like, ooh, just make that 1/2, right? I mean, you know, you can reduce the fraction to lowest terms. In some sense, factoring a group is kind of like that. You know, you're trying to reduce a group to its lowest terms in some sense. So if you have a group that doesn't allow factoring, except in the most trivial sense, right? Because you can always factor a group by the identity subgroup. That's just not interesting. If you look at the factor group by the identity subgroup, all that does is it puts every element in its own equivalence class. So it's basically just saying take G and wrap every single element in a pair of curly brackets and multiply like usual. So like G mod the identity is a horrible, horrible, silly thing that you can do, but we don't want to do. Ignoring that, if we have a group which does not allow a quotient, right? If it doesn't allow a quotient by a non-trivial proper subgroup, because also if you take G and divide by G, how many cosets? G mod G, 1 coset, right? We're back to the trivial group again. So either G mod the identity group or G mod itself, these are kind of not interesting coset groups, not interesting factor groups. So if you can find factor groups other than those two things, right, if it's possible, then that's an interesting factoring of the group. When that is not possible, we say that the group is simple. A simple group is one for which there does not exist a normal subgroup, which is a proper subgroup in a non-trivial subgroup, you know, a non-trivial, like it says right here. A group G is called simple if the only normal subgroups of G are E and the whole group itself. There, you know, it was a major project of the mathematical community over the past, I don't know, 100 or so years to classify finite simple groups. There is in fact a complete classification of such things, and the proof of which spans about 10,000 pages. Yeah, so we're not going to prove all that. One result called the Feit-Thompson result, which is relatively simple to state, the proof of that particular linchpin alone is 250 pages. I mean, so it's just a monstrous result, but pun intended. And anyway, I would point out that I love what we're talking about right now. We've just given a very technical meaning to the term simple group, right? That's kind of messed up, isn't it? Yeah. I mean, what's wrong with mathematicians? Why do we have to like co-opt ordinary English words and give them technical meanings, you know? Why can't we call it like the Versnarkschninknorken property of a group or something? I don't know. Make up some word nobody's using. Well, we got to use simple. But anyway, that's what they're called, simple groups. So you already know some simple groups. ZP, where P is prime, those are simple because they have no non-trivial. I mean, the only normal subgroup of Z mod P is 0 or ZP, right? So that's a simple group. And you can actually show that A sub n, the alternating group of order n, is a simple group for n larger than or equal to 5. However, A4 is actually not simple, but it's like a couple pages of gory calculations with cycles and stuff to show it. It would take us about 2 lectures to like really flesh that out. Just gory calculation. But it can be shown that A4 is not simple. It permits a non-trivial, non-proper subgroup, which forms an interesting quotient. This ultimately is an important fact for Galois theory when we study it next semester because, long story short, if you have a polynomial and you look at its Galois group, if the Galois group is simple, that means it's not solvable. When we say a subgroup is solvable, that actually means that the equation you're looking at has solutions in the sense of like a quadratic equation. So finding polynomials with simple Galois groups means that those polynomials do not permit solution by reduction to radicals. So it's an interesting thing. Yeah.
So on the example 14, you have n is
Uh-oh.
less than or equal to 5, and then it's greater than or equal to 5. So which one is it?
Greater than or equal to 5. That's supposed to be greater than or equal to. I don't know what's wrong with me. Greater than or equal to. Yeah. That one's right. This one, es no bueno. Now, this is an important observation. If we're in a factor group, and if we have A, AH, if A to the power K is in H, well, that means essentially that A to the power K is the identity. Well, A to the K times H is the identity if A to the K is in H. So what this says is that the order of the element AH in the factor group, it's the smallest K for which A to the K is in H, all right? Certainly, if you get to the order of the element itself, that will be equal to the identity, right? So if I have a representative of order 10, then for sure the coset which it represents has an order of no more than 10. So it just depends whether, earlier powers of that element actually are in H before, right? If I look at A and I square A and the square of A is in H, then that element that is an element of order 2. If the 5th power ends up in H, then it's an element of order 5. There's an unfortunate thing that happens here. We have used that to denote the order of the coset in terms of like set theory, and there's a distinction in concept here. The number of elements in this is just equal to the number of elements in H, but the order of this as a member of the factor group is a different thing. It's how many times you multiply this until it gets back to the identity coset, H itself. All right, finally, this is just a more interesting example here. I look at Z4 cross Z4, and I look at the quotient of this by a couple different subgroups. The one subgroup I look at is this H, which is basically 2Z4 cross 2Z4. I calculate the cosets, they're this, And if you look at it, you can see that every non-element of G mod H has order 2, which means it's a four element group. Everything has order 2 except for the identity. It is the up isomorphism, the what? Klein 4 group, right, or Z2 cross Z2. You could also look at this subgroup of Z4 cross Z4, 1, 0, 2, 0, 3, 0, 4, 0. That's another subgroup of Z4 cross Z4. And when you look at the coset space there, you get this, and it has an element of order 4. Like 0, 1 plus k has order 4, because if you take that and add it to itself, you get 0, 2 plus k. Take that and add it to itself again, you get 0, 3 plus k. Add it to itself again, you get 0, 4. You have to add this to itself, 4 copies of this to itself before you get back to 0 again, all right? So that makes this have order 4, despite the fact that, well, and unfortunately, this is not a great example for trying to alleviate that confusion, because this both has order 4 and it has order 4. Like there's 4 things in it, right? Now the previous one, each of the non-identity cosets had order 2, and they also had order 4, in terms of them having 4 things in them. Finally, so here's a recap. When we mod by that, we get this cross that. We mod by that, we get this cross that. Anything mod the identity is essentially just itself again. We take the group mod itself, that just basically goes to 0. And so the identity cross, so this up isomorphism is just Z4 again. And this is Z2 cross Z2. Uh-oh. Dr. Sprano. Ah, hilarious. Very funny. I'm going to end class early to go sabotage his class sometime soon. So you have that to look forward to. All right. And then finally, sorry. All right, anyway, so now I'm just flustered. Let's just stop it here.